Good morning. The chapter 1 and chapter 2 are just brief summary about the chemistry that you have learned in general chemistry. I will save my time and just briefly mention and briefly explain the structure and bonding and about organic compounds. There are many different kind of atoms in the universe. However, just a few atoms are the major components of living materials and organic compounds: hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, and some halogens. Because most of organic compounds contains the carbons, and carbon plays a very important role in organic compounds and also organic chemistry. The organic chemistry is a chemistry about carbon compounds. Why do we learn this structure and bonding? Because we'll talk about organic molecules. Organic molecules is made of atoms by making a bond. So the making a bond plays an important role in the overall structure of the molecules. So that's why we try to review some of the things that we have learned in the general chemistry. We all know there is a nucleus in the center and electrons around the nucleus. Electrons are negatively charged, the nucleus is positively charged. However, they not come closer. Actually, the electron is so small, and their existence is represented by the probability for the existence. And quantum mechanics describes the probability of small particles such as electrons. And actually, the probability function can be described by the wave functions. And those wave functions are the fundamental things of the quantum mechanics of an atom or small particles. Organic chemists are very interested in the electrons rather than nucleus. Electrons is negatively charged, but they don't collapse with a nucleus, positively charged nucleus, because the electrons are located in certain shells, and there are several rooms in one shell, and the electrons cannot penetrate those shells. Inside of the shells, there are different kind of rooms called orbitals. Depending on the angular momentum of an orbitals, we classify those orbitals as S, P, and D. And S orbitals and the P orbitals and D orbitals are shaped like this. Different colors represents different phase of an orbitals. S orbitals is spherical, but the P orbital has two lobes, and two lobes has opposite phase. There are only one kind of S orbitals, but there are 3 different kinds of P orbitals, and there are 5 different kinds of D orbitals. But in organic chemistry, S and P orbitals play most important roles, and D orbitals play an important role in metals. Therefore, we'll focus on S and P orbitals of an atom. Carbon is the most important atom in organic chemistry, so we'll start from a carbon. Carbon has 6 electrons. And if you look at the atomic configuration of electrons of the carbon, is 1s2, 2s2, and 2p2. Energy level of atomic orbitals can be described like this. 1s2 is the most stable one, and 2s2 and 2p2, they're on the same shell, but there are two different kind of atomic orbitals in the second shell, S and P. There's only one kind of s orbitals, but there are three different kind of p orbitals. They are called px, py, and pg. The electron's outermost shell plays an important role to make a bond with other atoms. If you look at the carbons, the outermost shell is the second electronic shell. The second electron shell has two different kind of atomic orbitals like S and P, and the P has three rooms. If the carbon atom wants to make a bond with other atoms, they will reorganize the orbitals in the outermost shell and try to make atomic orbitals try to make a molecular orbitals out of atomic orbitals. Therefore, the carbon has 2s orbitals and 3 2p orbitals, and they will hybridize each other and generate 4 molecular orbitals, because the number of atomic orbitals you used will be the same of the number of molecular orbitals you generated. Before they make molecular orbitals, the atomic orbitals in the outermost shell will be mixed each other and averaged out, and we call it hybridization. So you average out 1 s orbital and 3 p orbitals, and the average of those averaged orbitals are called hybrid orbitals. So you will generate 4 sp3 hybrid orbitals. 1s orbitals never get any change because they are inside of the electronic shells, and they are not involved in the chemical reaction, or they are not involved in the creating molecular orbitals. The most simple case for the making a bond is the making a bond between carbon and hydrogen, because hydrogen has only 1 s orbitals. If carbon wants to make a bond, the carbon will require 4 hydrogen atoms. It is very obvious that you will make a sp3 hybrid orbitals from carbon, and s orbital from hydrogen will make a molecular orbitals. So we call the molecular orbital between carbon and hydrogen is sp3 hybrid molecular orbitals, and we call and if the molecular orbital generated by hybridization contains any character of s orbitals, we call sigma molecular orbitals. We can expand this kind of concept to other chemical bonds. For example, if you look at the ethane, there are two different kinds of bond, CC and CH. As we talked about, the CH bond is sp3s sigma orbitals. But if you look at the carbon and carbon, we can see they are sp3 hybridized molecular orbitals, and because it contains less characters, we can classify them as sigma orbitals. But those two sigma orbitals are not the same. If you look at the ethane molecules, you can hybridize 1 s orbital and 2 p orbitals of the carbon, and you leave 1 p orbital without any mixing other atomic orbitals. In that case, 1 remained p orbital on the carbon will overlap with another p orbital on the other carbon, and will generate overlap of p atomic orbital and p atomic orbitals. Overlap of 2 p atomic orbitals will generate a molecular orbital, and we call that as pi molecular orbitals. If you look at acetylene molecules, CH bond will be sp hybrid, and you have one sp sigma molecular orbital between carbon-carbon, and two pp pi molecular orbital between carbon and carbon in the stellar molecules. And those sp orbital will have a sigma bond character, but two pp overlapped molecular orbital have a pi molecular characters. We can expand this kind of concept learned in carbon to nitrogen and oxygen. The only difference is the outermost shell electrons are the same, right? But the only difference is the number of electrons. For the nitrogen, you have 4 electrons in the outermost shell instead of 4 in the carbon. Oxygen have 6 electrons in the outermost shell instead of 4 in the carbon case. So we can expand the hybridization concept to nitrogen and oxygen. The only difference is the number of electrons, right? So the nitrogen, when the nitrogen wants to make a bond, they will just like a carbon, they will generate 4 sp3 hybridized orbitals and try to make a bond. Oxygen will also have generate the 4 sp3 hybrid orbitals. But for the nitrogen, you have 3 bonds and 1 pair of non-bonding electrons. So 4 sp3 orbitals will be split into 1 non-bonding orbital and 3 sp3 orbitals. For oxygen, you have 2 pairs of non-bonding electrons. Therefore, 4 sp3 orbitals can be classified into 2 non-bonding orbitals like this, and 2 sp3 hybrid orbitals, just like on methanol here. I just explained the relationship between atomic orbital and molecular orbital. Now we'll try to focus a little bit more on the concept of energy of the molecular orbitals. The simple example is the formation of molecular orbital out of 2 1s orbitals. 2 1s orbitals can combine by 2 ways. One, the phase of 2 s orbitals could be the same, and if they close each other, the electron density will be increased. If they overlap, and namely the orbital can be overlapped. However, if 2 atomic orbitals have the different opposite phase, then if they close each other, the electron density will be fade out. That means if they come closer, the overlap is not allowed. Overlap of 2 atoms are not favorable. So when we think about generation of a molecular orbital out of 2 1s orbitals, we can think of energetically more stable sigma bonding orbitals and energetically more unstable sigma anti-bonding orbitals. Actually, the molecular energy of the sigma anti-bonding orbitals will be higher than the atomic s orbitals, and the sigma bonding molecular orbitals will be energetically lower than the atomic s orbitals. In the case of ethylene, let's try to focus on pi molecular orbitals. And the pi molecular orbitals of ethylene is made from 2 p orbitals. If you have 2 p orbitals, there are 2 ways to combine them. You can make them the phase matched, or the phase could be opposite, right? If the phase are opposite, that means 2 atoms. It is not favorable to make 2 atoms come closer. But if the phase is matched, then those overlapping of two p orbitals will make two atoms come closer and more stable. So we can also think about pi bonding orbital and pi anti-bonding orbitals in the generation of pi orbitals from two p atomic orbitals. Some organic compounds are very simple, but most of organic compounds are very complicated. In some cases, organic compound contains more than 50 carbons, and the structure will, in that case, the structure will be very complicated. When you draw the structure of large molecules, it takes a lot of time. So it is better to draw the structure using the shorthand methods. Just if you draw a line between two atoms, that is 2 electrons, okay? So we can write the structure like on the left side. However, the line, it is very straightforward that the line represents 2 electrons. And we also know that all the carbon atom has one valence bond. Hydrogen has one valence bond. So even if we remove the lines, we can easily degenerate the line structure from the condensed structure. So we can just remove lines and draw the structure like this, the second one. In the second structure, you have one line, but because this is CH3, CH3, so we can shorten. We can have more short and structure like a CH3 right? So everybody knows. I mean, everybody can draw the original structure by just looking at the condensed structures. Another example. However, you have to be very careful about heteroatoms. In heteroatom case, never remove the hydrogens. Okay, but you can remove the lines, but never remove hydrogens, right? So, for example, you have a structure like this is what? This is threonine. This is an amino acid. You can remove hydrogens. Also, you can remove carbon also. But in order to represent that you have the carbon there, you should create an angle, right? So the structure on the left can be shorthanded like the structure on the right. Chapter 1 describes that organic chemistry is the chemistry of carbon compounds and the relationship between atom and molecules, the importance of the bond in the molecules. And the bond can be described by the molecular orbitals. And we also talked about the ground state energy level of the molecular orbital and the excited state energy level of the molecular orbitals. If we talk about the molecular orbitals, and if the bond contains any sigma characters, any s characters, then we classify that molecular orbital as the sigma bonds. If the molecular orbital is 100% p orbitals, it consists of 100% p orbitals, overlapping over p orbitals, then we call pi bonds. We can expand this kind of concept to nitrogen and oxygens. Here's work of the problem. That's electron dot structure for the acetonitrile, okay? So you have 2 carbons and try to draw it, okay? But I think it will be like a CH3CN, probably is the structure for the acetonitrile. Okay, that's the about chapter 1. Thank you. Bye.